Welcome friends, let's solve this differential equation by using series. A bit of a different approach likely than you have seen before. So y prime equals y of 0 equals 1. We have this initial condition, and we have a MacLaurin series. It goes from 0 to positive infinity, and then you have the nth derivative evaluated at 0, x to the n over n factorial. Okay, so this stuff is constructed in other classes. Look at the pieces that we need here. Right? When you expand this, what do you have? Well, you would have, for example, like 0, begin with 0. That's just the value of the function at 0, and this would be x to the 0 over n factorial, like this, which is just 0 factorial in this particular case. Then you would have basically the first derivative this way, right, evaluated at 0, okay, and then x to the first, and this whole thing then would be over 1 factorial. Then you would have, if you wanted to be very explicit, f, right, and up here you put out 2, that means the second derivative, and then, or f double prime if you want. And then you would have that evaluated as 0, and then x to the second over 2 factorial, right? And then you would have f up here 3, so that means the third derivative evaluated as 0, x cubed, and then divided by 3 factorial, and then plot ... Anyway, so you get this expansion, right? If he works with this first thing is really just 1. Think about it. 0 factorial is 1. The value of the function at 0 is 1. You see? X to the 0 is 1. The first derivative for now, well, let's think about this for a second. It's equal to y itself, isn't it? Look at it. Y prime is equal to y, so you know it essentially. It would be like saying, in this particular case, it would also be equal to 1, and then x to the first is x, 1 factorial is 1, doesn't change anything, plus. Now, we don't have the second derivative given anywhere. That's okay, we can very likely find it simply by doing this, right? Like y double prime. If you differentiate both sides of this, then y double prime would be equal to y prime. But we know that y prime is also equal to y, and then we can evaluate all of this as follows. So in other words, y double prime of 0 would just be equal to y of 0 in the first place. So that's just equal to 1. So that means now you're going to put here 1 over 2 factorial and then x to the second. Okay, it's going places. Look, what about y triple prime? Well, how do you form that? You just differentiate y double prime, don't you? Like this. But then that's just equal to y prime, which is ultimately also equal to y again. So for that reason, you can just write y triple prime equals y, which means y triple prime at 0 is just y of 0 again. So the next term that we get would look like this, plus 1 over 3 factorial, and then x to the third, and then you can repeat this process like that, okay? Forever and ever, pretty much. So in other words, we get this, and once you clean it up, 1 plus x plus 1 over 2 factorial, right, plus, and this is an x squared over here, and then plus 1/3, and then x cubed, plus ... This series here is a well-known series, hopefully. It's e to the x. In other words, what this tells us is that y of x has to be equal to e to the x, as shown. That's the solution. I'm not sure whether you've seen this particular approach using series to solve equations, differential equations. Maybe have, maybe haven't. But repeatedly differentiate and then plug in and evaluate, generate the coefficients, like the one up here, the one over here. And then you plug into this pattern and you get the solution before you know it. Okay. Leave a like.